Hey, so I had a really cool moment in a class I had on this last Sunday. It was my AMC 12 prep class. By the way, if you are interested in trying a class out, you're welcome to sit in on one class and you don't owe anything if you don't like the class. Like you can just sit in on one and see if it's for you. But I was sitting in the class and we were going over a problem from the 2015 12B. It was problem 7. I think that was the test. And we went through the problem, and then I kind of started thinking about it and was trying to decide if the idea inherent in the problem was a small notebook concept or not. So if you don't know about small notebook concepts, it's the key ideas that we learn that may or may not be able to give us an edge during the test. So my small notebook is here. The video called The Small Notebook Justified and explained, I think, something like that. But it's called I'll put it in the description down below. But basically, it's a lot of key ideas that you might use throughout the test. And the book that I recommend is one by Moleskine. You can't really read it; it's too not good enough font. But I will link my website, and you can go to the resources page. It's the first item on the resources page below the AOPS books. So they're basically key ideas, things that when they come up, they could save a lot of time. They don't all come up all the time, but they should have been coming up on the test more than once usually. Something like the N-ray partitional from 2011 10A problem number 25. That's a one-off concept that's never appeared before or since. I don't recommend putting things like that in it, but rather things that have made repeated appearances and things that could save significant time. So if you saw there, I just showed you the a regular tetrahedron height is rad 6 over 3 times x, and the volume is x cubed root 2 over 12. So it kind of, if you can just shortcut that process, it's nice to have those little things memorized rather than have to derive them during the test. And granted, I can derive them too, but if I have to do that, it might take a minute, and that's a minute less than I can spend on something else. So anyhow, we were going through a certain problem, and it was kind of really neat. The A small notebook concept was born from it, and I thought I would share that all with you. If you are interested in this year's small notebook classes, um, I will have them announced soon. This year's format is not going to be a single day. It's going to be a 4 week seminar. The first week will probably be in the next 2 weeks. I will start a class when it gets to 10 people, and I will start another one if it gets to 10 more people after that. It's going to be 4 weeks, each 2 hours long. I was finding that when I did 4 hours, one single session, I was racing through as fast as I could, and I still couldn't get through all the concepts. And students are writing very furiously. And I even added free time to the end, making it 4.5 to 5 hours sometimes for the class, and it still wasn't enough. So this year I decided to make it a multi-day experience. If you're interested in that class, reach out to me through my website. The description on the small notebook class is probably not accurate. I'll probably try to update it soon. But for now, when you're trying to ask yourself when you're studying, how do you know what to add or what to write, or how do you think of the things to write? That's what this video is about. You'll kind of see a very live, organic process. I've never known this concept that I came up with during the class before this. I wasn't recalling information. I was exploring after the problem was done, trying to see what happens out of curiosity. The best math students are often curious about the concepts that they're working on, and they wonder, why are these working? And so I highly encourage you, when you're doing your problems, when you're doing past contests, don't just look at, is it right? Is it wrong? And that's all that matters. No, there's so much more than that. There's efficiency of your process. There's the deeper implications of the problem. There's the question about whether or not this concept could come up again, and how would I recall it? How would the concept get upgraded in the future era? So here's an example from my class. Again, reach out if you'd like to sit down on one class at no cost. And then if you wanted to keep going, of course, you can talk to me about that as well. With no further ado, here we go. Like 16 or something. A regular 15 gon has L lines of symmetry, and the smallest positive angle for which it has rotational symmetry is R degrees. Okay, so first off, 360 over 15 is 24. That's your exterior angle. Meaning if I go here and I want to start my next piece, I would go a dotted line, I would make 24 degrees. That would be my next. That would be 24 degrees. That's my next side, like A, B, C, like this. That sucks. I would probably have to think. Let's look at a three-gon, commonly known as an equilateral triangle. It's going to have a line of symmetry through every vertex. Those are going to be its only lines of symmetry. It would have three. Makes me think a 15-gon could conceivably have only 15 lines of symmetry. It makes logical sense. It's not like a hexagon where you can split the sides in the middle and get a line of symmetry. You can never connect the vertices on a 15-gon, just like you can't do it on an equilateral triangle because there's no opposite vertices. So this is why they chose 15 for this problem. Because it's who's going to draw this? You draw a whole 15-gon, have fun. That sounds like suffering to me. What they really want is, can you realize maybe I could do cases of 3 and 5, learn from what I can observe from those, and I would choose these specifically because that's an odd number. The rotational symmetry is what's interesting too, is that the angle made from the center, by the way, that angle is also 24 degrees. So your exterior angle and your central angle are identical. And you're just going to add 24 and 15. And you're going to get 39. Wow, I feel good about myself for that question. Like I just did a good job. Like sometimes I'm like not that swell. And then this time I'm like, it's all this caffeine I've just had. I sipped like half of my cold brew and now I feel like Superman brain powers or something. Does it make sense though? Honestly, the key ideas here you want to remember are going to be, if you get something with like big numbers, make a smaller, similar type of situation and think about that one. Because I have a odd number of vertices, I could never pair all of the vertices, so there could never be an opposite vertex. I mean, this is the kind of question you almost want to ask. Could it become a small notebook concept? It could, but how often realistically are we doing symmetry with odd numbered n-gons? An n-gon is just a polygon with n sides. We're just not doing it that often. It's an obscure thing that I don't know. Maybe it's come up twice in the 25 years. Yeah, I probably wouldn't judge anyone who wrote it. I can't even say you shouldn't write it. Maybe you should. Some people have better memories than others. Um, but yeah, but even in fact, I almost want to write it now. For n-gons, if n is even, you probably have 2n lines of symmetry. Oh, no, you wouldn't, because some of your lines of symmetry are doubled up because you're connecting vertices. So what you would have, let's say hexagon, for instance. Ooh, wait, is there always n lines of symmetry? Hold on a second. Because you have 1, 2, 3, and then you have 1, 2, 3. What? That should go in the small notebook. All n-gons, I gotta look it up now in a second. I'm drawing a conclusion. We're gonna Google search this. Ask ChatGPT. All n-gons have n lines of symmetry. Regular n-gon. Okay, this is it. We're gonna go look. Did I just have a genius moment right here? These things happen about once or twice a year for me, and I'm pretty thrilled right now. Definitely ordering coffee from this place again. Give me a moment. Do all regular n-gons have exactly n lines of symmetry? Resume. Yes, all regular n-gons. Look at that. This is how you study. Okay? When you see something and it seems peculiar and interesting, look at how simple of a statement that is. That goes small notebook. Now that goes small notebook. If it had been separate rules for odd and even, I would have been on the fence. But because it's so simple, n-gons have n lines of symmetry. That's just beautiful, brilliant, and simple. You don't have to even, you'll probably never forget it again, even if you try. You'll like go to sleep for the next 4 months and then you'll wake up like, I don't know, what are we at? September, so you'll be 13, you'll be the January 7th, and you'll be like, oh my gosh, all n-gons have n lines of symmetry. And you'll never forget because this is such a weird thing. It's almost like 3, 4, 5 right triangles. I don't know anybody who's ever forgotten that since high school. Like you could be 20 years later and you'll still remember 3, 4, 5. Um, yeah. Really fascinating actually. I'm gonna write it in mine right now. I was gonna like not write it and then I better write it. Um, okay, so even for those of you that got this one right, because only one of you asked this question, I do want you to pull away from what we just did the idea that it kind of goes back to the video I have that says stop getting your homework done. And what I mean by it is stop doing your homework for the purpose of completing the task. Right? We complete the task and we're done. That's not what we want to do with homework. Your homework is a time to like dig deeper, to really think about these things. Why is that happening? Right? When it's a 15 gun and it has 15, it's kind of peculiar. Maybe we could ask questions like what would happen if there were an even number of sides? And for a second, I was thinking that you would get twice as many because every vertex would do it and you'd also cut each midpoints of the opposite sides. But then you realize you're doubling up the lines of symmetry and it's actually just n. So 195 195. All regular n-gons have exactly n lines of symmetry. It's also interesting that the odd ones only have the line through the vertex that passes through the midpoint of the side opposite, whereas the even ones have midpoint connections and vertex connections. I'm not going to note that in this small notebook. You want to write as little as possible there. Let's go back to here. AMC 12 2015B. Okay, cool. Maybe I will make a video of this and call it the making of a small notebook concept. Sounds good, right? Because we're recording. It's just I always regret not recording because there's sometimes I say things that are good and then I'm like, oh, that was really good. You should have recorded that. And then it's not recorded and I forget what I said and life goes on. We move on with our lives. Let's continue.